Yeah, so we have Owen Siyoto.
Good afternoon, everyone. Thank you. Thank you. Okay, let me try to share my screen.
Okay, we.
Okay. Can you guys see my screen?
Yes, we can see your screen.
Okay. So we may start, but I can just give a brief introduction of myself. I'm Owen Siyoto. I work for the Zambia Statistics Agency, short form ZAMSTATS. It used to be called Central Statistical Office. That's probably what you might be familiar with. I'm a data scientist there. Though, like many of you, I didn't go directly as data scientist. I was working as a statistician. Then I went into this field because my motivation was how we can incorporate data science or AI into official statistics. As you may tell, the Zambia Statistics Agency is the agency in charge of official statistics in our country. And we've got such offices in every country. In South Africa, it's called Stats SA, ZimStats, so we've got such offices. My topic is the use of transfer learning and region regression on satellite images to predict poverty in Zambia. And I'm sure you can tell from the topic, poverty, because I'm an official statistician and such a topic would be interesting to me. And I must say that I'm grateful to the organizers of the Indaba for giving me this opportunity to share, for giving us this opportunity to interact, to share ideas. And furthermore, I would also, I also want to thank the previous speakers, Francis, Dr. Piri, and Jonathan, because a lot of you have made my work much easier already. You've covered stuff like AI, machine learning, transfer learning, CNN, ImageNet. So that means I'll not do a lot of explanation. I'll just be sharing a lot of images and people will be able to follow through. That said, please allow me to start the presentation. Okay, this is an overview of the presentation. The goal of this research was to estimate the wealth index in Zambia with the help of machine learning and remote sensing. Remote sensing, I think it was mentioned already. This is the information that we get from, in simple terms, the information that we get from satellite images. So, subject is the estimation of the wealth index using machine learning in Zambia. And the motivation is that 700 million people, or 11% of the world's population, are still living in extreme poverty.
Sorry, Owen, I'm not sure if you're sharing just a window, a specific window. We can only see the documents, the zipped documents in the background.
Oh, okay. Let me try to. What can you see now?
We're still seeing the zipped documents.
The zip document?
Yes.
Okay, let me try again. How about now?
Yes, now we can see the we can see a PDF document.
Okay.
Yeah.
Okay, you can see.
Yes.
Control L. I'm failing to get into the full screen. Okay. So you can see the full screen now?
Yes, yes, thank you.
Okay, so the motivation, I repeat, the motivation is that 11% of the world's population still live in poverty. And also in Zambia at national level, it is believed that 54% of the population are living in poverty. And also at national level, we are able to provide data at lower administrative levels. What I mean lower administrative levels is, the way Zambia is, we've got provinces, and these provinces are divided into districts, constituencies, and wards. So in order for us to make proper policies to target poverty, we would need data at the community level, at the low community level. In this case, the ward level data would make sense because a ward is represented by a councillor administratively. So that's what I mean. And we don't have such information. So to further illustrate my point, I've put two maps of Zambia. The one on the left, don't on the screen, but one map shows the boundaries of the provinces. And the other map shows the boundaries of wards. In order for us to make meaningful decisions that would reduce poverty, we need the map which is at ward level. So we can only provide information using traditional means, using the map on the left, the one at provincial level. Further, in the I show a picture where we have my colleague, her name is Chisua, collecting data using traditional means. So we have to go face-to-face interview and interview a respondent. And they give us some information, we collect information on various characteristics, which we eventually use to calculate the poverty. And on the right, we've got some satellite, and it's just collecting images by it being a satellite in there, maybe for other purposes. This information can be useful for our users, for our purposes, as we demonstrate as we go on. Further, I show a picture. You see from the sky, you can see that one image shows some picture of some shanty compound or some, let me say, not so rich area. And then the one on the right, on the left, shows a picture of some area which is poshy and seemingly rich. So from the sky, you're able to tell that one area looks poor and one area looks rich. And we can take advantage of that and teach our machine learning algorithms how to make such predictions. Another assumption that we're going to use in our discussion is the fact that at night, places that are richer tend to be much brighter than the ones that are dark. Of course, I know that in some places with national parks, but it's generally true. Europe looks much brighter than Africa. And we know South Africa looks much brighter down there compared to the middle of Africa. And of course, we know that South Africa is doing better economically than our countries. Then we move on to the sources of data for analysis. The sources of data were mainly three. We have data from the Demographic Health Survey. I'm not so sure if you're familiar with this data, but this data is from what is called as the Demographic Health Survey Program. It's a main source of data in developing countries. It mainly collects data on health indicators, but also from this data we collect, they compile something called the wealth index. So the wealth index is something that ranks a household from from some minimum to a maximum based on the amount of assets they have. Then I got images from Google, and then the other source of data on the nitrite intensity, which I'll discuss later, was gotten from National Oceanic and Atmospheric Administration. So all these sources of data, I was able to get them for free. So I used open source software and open source data sources. Though Google you might have to pay, but at that point I did trial okay. So sources of data, the DHS. Like I said, the DHS is part of the Demographic Health Survey program that collects data in 90 countries. And so far they have over 400 surveys. Like, we know what a survey is. Though we are data scientists, but we know what a survey is. We select a sample, and out of the whole population, we select some sample which we survey and collect information on. So the DHS is a two-stage stratified sample design, and they collected data in 545 clusters. So what they do is they demarcate the whole country. Some country, generally not only Zambia, but all countries, will be demarcated into smaller units, which are easily handled by an enumerator. So these are usually called clusters or primary sampling units. So we collect information from these clusters. Okay. I need to pause and answer some questions, or can I go on? Okay, something else. So, like I said, in each cluster we usually select 25 households, and then this means that our data set, the DHS data set, had 12,831 households. So the data set, as I mentioned before, it provided us with the wealth index, and it is a continuous variable which ranges from negative 102, 153 to 295,653. So negative 102,153 is the minimum, and the maximum is 295,000. It also provided us with the latitude and longitude from whose satellite images we were able to download, which we used to download the satellite images that we used. So this is the information that we got from the DHS. In this map, I show the points where the DHS was conducted in Zambia. So as you can see, the sample was spread throughout the entire country, and more sample points were actually around Lusaka for obvious reasons, because Lusaka has the biggest population. We move on to the methodology. So what we have is we create a linear chain transfer learning graph, where the first problem is something that is done from the object recognition on ImageNet. Luckily, I will not have to talk about that because Jonathan already tackled it enough. Then the second problem is the P2, which is predicting the nitrite intensity from daytime satellite images. And as we are doing that, we are also learning features that are useful for poverty prediction. We'll talk about that later, I'll demonstrate more. And the third problem is predicting poverty from the daytime images using the features that it learned in the previous step. So we now going a bit detailed into the steps. So like I said, we have the map of Zambia there, where we have points from which a survey was conducted. So these points provide us with the latitude and longitude from which we're able to get Google daytime images, the images for the day. And then similarly, we're also able to get nighttime data images. I mean, not images, in nighttime intensities. So the idea is that we want to teach the CNN on how to predict nighttime intensities, like I mentioned in the previous slide. When it learns how to predict nighttime intensities, it will automatically learn it will automatically learn features that are useful for poverty. What I mean is this, like I said, a rich place at night would be bright. A more medium place would be, medium poor would be medium bright, and a much poor place would be dark at night. So the network will learn some features which are why it is classifying, actually this is a classification task, why it is classifying a particular satellite images to be bright, to be medium bright, and to be dark. So that is the whole idea. So this is not an explicit supervision. It just learns the features. Then in the second step, after the features are learned, then we use a tuned model. We tune a model. I think this term might have been used already. We use a tuned model. You know, this model that we're training here will be tuned. So we use a tuned model to now extract features from all the images. Remember I mentioned these images, the number of images. So we extract features from these images. So we have, when we do this, we extract a feature vector of 4,096 dimensions. For these total images, and representing 535 clusters. You might be wondering why we're 535 when I mentioned 545. We dropped 10 clusters from the analysis because those 10 clusters didn't have nitrite intensities. So that's what happened. And then once we get the features, we now pass the features into another algorithm, which is now the ridge regression. Of course, why we use the ridge regression is, I think I heard someone mentioning overfitting in the morning. So we use the ridge regression because regularization will prevent overfitting. Because you don't want to have a model which is overfitting, because that's a useless model. So we pass the trained features through the ridge regression. Remember, each one of these points has a worth index. So we are using that worth index from each one of those points now to train a model using those features. Because those features will be related to a particular cluster, which is what we do. Then in the final step, all that we need to do is we just get an image from any area in Zambia and pass it through the pipeline. Then what we get on the other end is a worth index. So by so doing, we aggregate this and then would have solved the problem of estimating poverty at what level or at a smaller level. So in the next slide, I'm happy also again, this was tackled by Jonathan. I'm showing some visualization. So this is some urban areas. And then as the model is predicting the nitrite intensities, this is what it is seeing. So it sees this, and then whatever it's seeing, it will be able to interpret that this is an electric power line, this is a well-organized neighborhood. It will be able to see a lot of things. And whatever it sees, it will use those things now to try and relate it to poverty. I show a similar image for the rural areas. What you see is some activation for some river here, some path. So the CNN would make sense out of it. And then we move on to the evaluation of metrics. I heard Dr. Piri again mention this. So because of the nature of the debated variable that we are having, a continuous variable which is running from whatever, the metrics that was chosen for this analysis was the 5-fold cross-validation R-squared matrix, which is a statistical measure that presents a proportion of the variance for the target variable or the dependent variable. We can use them interchangeably. In our case, it was the worth index that is explained by the independent variables. So it usually ranges from 0 to 1, and it's commonly stated in percentages. And then we further did a randomization test just to make sure that the results that we obtained were not as a result of statistical chance. So what we do is we randomize the labels. After we randomize the labels, give them junk labels, and then we do another test. So I'll show you the results in the next slide. Okay, so this slide was just showing the relationship between nitrite intensity and the worth index. As you can see, there's some relationship, some linear relationship. But nitrite intensity alone does not explain the worth index. As you can see, there are some points which are off the line, which is why we had to use the transfer learning, so that it just helps us to train the model. Otherwise, many people have tried to predict nitrite intensity straight from the related nitrite intensity with the worth index, and the results haven't been so good. And these are the results that we obtained. I got the R-squared of 0.55. And then what you're seeing in this, what you're seeing on the right is the results of a randomized test. So you see the model is predicting somewhere here, but the randomized one are just somewhere here off. So which shows that the model was really working and it wasn't as a result of statistical chance. And further, I show more results here. So on the left, we have the actual worth index, the average per province that was predicted, that was captured from the survey. And on the right, we have the one that our model predicted. And as you can see, they are quite close, with a few variations here and here. And we show the table here, like according to the data set, Central Province had the average worth index of 19,142, and the model predicted 16,000, just like that. So in conclusion, the ML, the transfer learning approach and regression was used to estimate the worth index. And as you can tell, this is a real data set, not a toy data set. And we got a worth index which is quite okay, 0.55. So I think with a few improvements in this model or this kind of analysis, and as we continue creating more knowledge and learning more technology, such an approach can be used to solve that problem of lack of data, because I'll tell you, working from a statistical office, that the cost of having data at ward level or even district level is unimaginable, and the statistical offices like the office where I work cannot simply provide that information, which is key for decision makers. So such approaches in future would be useful to make such estimations. Unfortunately, because our field, AI, deep learning, machine learning, is still quite new, I've tried to make a few presentations, and not so many of my colleagues fully understand what I'm talking about. So I think with platforms like these ones and such interactions, a lot of people will become aware of the power of AI and ML, and in future we can incorporate it in our statistical systems. So having said that, we are at the end of my presentation. So perhaps I can hand over to you. So, are there questions or?
So I'm hoping. Okay, so we have a question from Jonathan. So if there are any other questions, just kindly just type them in the Q&A. If you're able to access the chat, just in the chat, so that we can have questions around this. This is a very interesting topic, like looking at how it's quite unlikely that would actually get to realize that we can really predict poverty by just looking at some of the features that you mentioned. So coming to Jonathan's question, so he's asking whether you used data from other countries to improve the model for Zambia. So the survey has data from, does the survey have data from other countries? And then we also have another question from Jonathan as well, asking whether there is a public map of the wards in Zambia. So he couldn't find one when he tried a few years ago, and was told it might be hard to get access.
Okay, let me start with the first question. Yes, I know there's some research. Actually, most of this work was based on some work done by John from Stanford University. And those guys tried to analyze several other countries. I think they did Uganda, Nigeria, I should think even Malawi. But then they did an experiment where they tried to combine the data from several countries, and the models were like, the combined data was not working well for the models. They came to a conclusion that it's better to use the country-specific data to train the models. So in this case, that's why I also just use the data for Zambia, from the ZDHS for Zambia. And also probably there could have been differences in terms of time, the time space. Some countries would do a data in a particular year, other countries in a year. So all that challenge would have come about. Yes. So it would have required maybe further adjustments. With regards to the word shape files, you mean the word shape files, right? Yes. With regards to the word shape files, I think, if you request, I can tell you for a fact, if you request our office, you write to the Statistician General. He would be able to refer to the specific unit, in our case the GIS unit, and they can provide that data set. But I think I should tell you that at the moment, I'm not so sure if the word data set would be available because of the elections. It's still confidential. But the 2016 one, like the one I used in this research, would certainly be available. And it's available to the public. Yeah.